So good evening, everyone. This is the third of our 4 sessions organized by the Royal Aeronautical Society in conjunction with the Coventry University. Last time when we met, we looked at Plane Maker and created a fairly rudimentary aircraft. There are quite a few other tools available within the X-plane environment, such as Airfoil Maker, that allows us to model the aerodynamic behavior, as well as other third-party tools that allow us to generate objects that can be used in the scenery of X-plane. We've had a very rudimentary introduction to Plane Maker, and we looked at a fairly elementary design, which we are going to go over again just for sake of completion. So anyway, I'll make a start. There will be some files needed for the session. For people who are present in the class, the files have been uploaded to their desktop. For the people who are live online, these files will be dropped in the chat box, so you are able to download them and use them during the course of the evening. Okay, so let's make a start. I'll share my screen. And we were looking at Foil Maker, and in particular, XFLR5, which is a very nice tool that can assist us in modeling some of the aerodynamic behavior. Okay, we might also look at some of the tools that I have developed that will perhaps reduce some of the burden when we create the files needed for X-plane. So without further ado, just a quick mention. The last session, which will be hopefully conducted in May, on the 17th of May, will be on our flight simulators here at Coventry, where it will have given you people, whoever signed up for that live session, enough opportunity, enough time to design either your own aircraft and come along and fly it in the sims, or improve the basic aircraft that was given to you in the second session. So you'll have plenty of time to perfect or to work on your designs. Just to very quickly go over the basic design elements that we had for the aircraft last week. We had an aircraft we're aiming for around 850 kilograms, 10 square meter wing area, span of around 7.7 meters. We weren't going to have anything clever with the wings, so it was a planform wing, so no taper, root chord the same as the tip chord. We weren't going to have any dihedral, etc. So just to prove that in reality this aircraft will work as well, we made some tiny models and we've flown them and they fly quite well. So the thing is fairly scalable as well. We also looked at, from a stability point of view, the requirement for the CG margin to be around 10% of the mean aerodynamic chord. And we also put down some very rudimentary empirical values for the empennage design, as well as for the fin design, and also for the control surface design. In fact, most of you were able to fly the aircraft. Some of you had an issue with starting the engine on the ground. Again, if people are still having problem, then if you post a comment on the chat, Matai, he is present with us. He will be able to answer those questions as we go along. what we needed for our aircraft design was the definition, the aerodynamic definition for the wing as well as for the empennage. For the empennage, we chose a NACA symmetrical aerofoil, and for the wing, we chose the NACA 2410. 10% thickness, 4%, 2% camber at 40% thickness. So fairly straightforward. But we needed to have created that airfoil, which didn't exist in the standard explain directory of airfoils. So how do we go about creating those airfoils? The best option is for you to use Airfoil Maker. So when we use Airfoil Maker, it requires us to create this lift coefficient versus alpha, the drag coefficient versus alpha, and the pitching moment coefficient with alpha. X-plane requires these three polars to be created between minus 180 degrees to plus 180 degrees. So how would this data come about? In normal use, it is unlikely that you're going to be flying the aircraft backwards, i.e. the trailing edge of the wing to be pointing in the free stream. So that's unlikely. But for X-plane requires the entire 360 degrees to be covered. The data can come from one of many sources. We can use X-foil. X-foil allows us to then import the geometry of the airfoil and produce the analysis that will give us the lift, drag, and pitching moment characteristics for the desired range of alpha. The major issue with X-foil is, as I was saying, it requires data between minus 180 to plus 180 degrees. It can be created using X-foil or using XFLR, or we could create this data manually. So what we're going to do today is we're going to have a little play around with X-foil to see how we are going to manipulate the data within this environment. And you'll see that it relies on inputting for the various curves, the minimas, the maximas, the slopes, and also how the curves inflex, etc., by putting in the various powers, effectively making it a curve fitting program. So it's a very elaborate curve fitting program that allows you to fit various curves. So the issue, as I said, is essentially it's very cumbersome data entry. And if you try to get the data from minus 180 degrees to 180 degrees plus using a CFD package, if it is a non-symmetrical airfoil, when you invert the airfoil, i.e. at minus 180 degrees, sometimes it doesn't converge. So in fact, convergence becomes a real issue with CFD packages when you try to run the airfoil back to front. So it is a bit of a problem. Flat plates and symmetrical airfoils, convergence is possible. For normal airfoils such as 2410, etc., things are going to be pretty tough. In fact, we tried it this afternoon. 2410 doesn't converge beyond 60 degrees. So it's a real tough ask. But anyway, we still have to satisfy X-plane's requirement between minus 180 and plus 180. So we need a better method. We need a better method of creating those airfoil files for X-plane. So what I did some years ago was to read the explain airfoil files and created a mechanism where I could import the lift, drag, and pitching moment curves as a set of data and import it and create the file for explain. Now, just a note, explain does not create the data dynamically from the constants that are used for generating those curves in Airfoil Maker. It merely uses the table of alpha, CL, CD, and CM and interpolates between those values. So it is possible to directly create the .afl file used by explain. And that's exactly what my program will do. So we'll give you a demo of both. So we'll first use Airfoil Maker and see what the data looks like. And then we'll use my program, and then we'll see how we can progress to the next stage. So if I minimize this and invoke Airfoil Maker, I can open any airfoil I want. So from the list of airfoils, there's a NACA 2410. So what is presented to you is the polars for various Reynolds numbers. So the first thing that you note is on the screen, there are two tabbed notebooks. The bottom tabs relate to the various Reynolds numbers. So you'll see multiple graphs in green. The greens are your lift versus alpha curves. The red graphs on the screen are the drag versus, or drag coefficient versus alpha, and the yellow is the pitching moment coefficient versus alpha. On the left-hand side of the screen, you will see some numbers. These numbers will allow us to modify the behavior of the curves of the airfoil. Clicking on the tab notebook will let us see the curves or the polars for various Reynolds numbers. So here we have 0.05 million, 50,000 to 1 million Reynolds number. So there are 5 curves, and you can see them. And as we move along the tab notebook, the appropriate curve will get highlighted. So that will be a solid color, whereas the faint color would be the other Reynolds number ranges that the airfoil file has. So this particular airfoil, the 2410, has 5 Reynolds numbers defined. So how do we change any of those parameters? The second tab looks at various angles of attack. So we can look at the entire range between -180 to 180, or we can look at plus minus 20 degrees. We can also easily look at lift to drag ratio. But let's concentrate on getting the basic data in. So let's say that you wanted to create the data for a high Reynolds number. And let's say that you had those curves available to you. The first parameter that you need to change is Reynolds number in that box by changing those spinners. We can change or set the Reynolds number. We're not going to do that for now. But let's say if you wanted to change the lift characteristics, then the intercept at the moment is going through 0. The slope has been defined. So if I increase the slope, the lift curve slope changes. If I change the maximum CL or reduce the maximum CL, that's the effect. So what you're able to do is by changing those constants, manipulating those constants, you are able to change the characteristics. It is often a time-consuming job to enter both all the pitching, drag, and lift characteristics for the airfoil for the entire range. Similarly, we can look at the drag. The drag curve is characterized by various parameters, such as the minimum CD value, the minimum CL value for the CD. Then you have other things like the drag bucket, the width of the bucket, the depth of the bucket. Now this is the area where you will get very little drag for an increase in lift. So generally speaking, it doesn't happen in practice, but it is there from a theoretical point of view. Similarly, you can define the characteristics for the pitching moment as well. So for example, if we change the bucket width for the drag, you can change the minimum or maximum drag value by clicking on those spinners. You can modify the stall behavior. And of course, you can modify any of the pitching moment characteristics in terms of the various slopes. And as you all know, that the partial derivative of the pitching moment coefficient with respect to the lift coefficient, i.e. partial Cm over partial Cl, must be a negative number, i.e. that slope must be negative for a stable response. So that would be one of the requirements for stability. Now you'll appreciate that creating the aerodynamic data using curve fitting is probably not a very good idea. I've been using X-Plane for a very long time. And generally speaking, when we design an aeroplane, we like to investigate its performance in straighter level flight generally, and also at moderate alphas. Obviously, we don't like to stall the aircraft. We may consider evaluating the aircraft at some negative incidences, but certainly not beyond 10 or 15 degrees. So in reality, if you can generate data between -20 to +20 alpha for both the lift, drag, and pitching moment, you will get a fairly robust simulation in X-plane. So the way I approach the problem is I will take a symmetrical aerofoil as a standard aerofoil, such as NACA 009, and then modify the data between -20 to 20 for the airfoil that I want to use. The rest of the data beyond -20 up to -180, and after 20 degrees plus to +180 degrees, a flat plate is as good an approximation to the airfoil that you have. So you don't really need to generate the data beyond -20 to +20. Now that gives us a bit of a fighting chance because most CFD packages should be able to generate the data between -20 to 20 with fair degree of accuracy, and convergence is highly likely. Okay, so as I said, this afternoon I tested the 2410 and it wasn't converging at high alpha. So what we need is a mechanism where we can edit the airfoil file directly. So now, next thing I'm going to do is show you what this airfoil file looks like in data format. Okay, and that will then allow you to manipulate that file directly if you wanted to. So most of you will have this file in the directory So that's what the airfoil file will look like. Now, just to reiterate, what does X-plane actually use? X-plane will use the thickness of the airfoil, which turns out to be the fourth line in the file. That number is the thickness of the airfoil. We're using a 2410, so it's 10% thick. The next line that X-plane uses is the drag divergence Mach number. Okay, that it uses, so it must be present in the file. Then follows a couple of columns of numbers which it uses for curve fitting the data. Again, we're not going to be bothered with that. The next number that appears in the file is the number of polars corresponding to each Reynolds number. So as you saw, 2410 had 5 Reynolds numbers defined. So that number basically relates to the number of individual polars for corresponding Reynolds number. Then comes 25 numbers, and these numbers are the constants used for curve fitting. And as it turns out, the second number there is the Reynolds number. Then comes the alpha minimum to alpha maximum, so -10 to +15. And similarly, there are other numbers corresponding to the curve fitting. But the saving grace is, once the airfoil file has been created, explain only uses the data table present below. So directly below that line of constants which are needed to generate the curves whilst you're in airfoil maker, once the file has been created, then these constants are no longer needed. Explain goes directly to this table. Now you can see the data starts at -180 degrees, and if you scroll down the file, it will go down all the way to +180. And then you have another line. This is now corresponding to the second Reynolds number range, that is at 100,000, okay, followed by the table for alpha, CL, CD, and CM. To change this file, if you wanted to just change the data, remember that from -180 degrees to -21 degrees alpha, the data is in increments of 1 degree. From 20 degrees minus to 0 degrees alpha, the data is in intervals of 0.1 degree. From 0 to 20 degrees, the data is again in intervals of 0.1 degree. And then from 21 degree plus to 180 degrees plus, the data is in 1 degree steps. Now that makes it a total of 721 data points. So explain then uses to interpolate between alpha when it runs the simulation. So what you're able to do is rename the .afl file. So whatever airfoil file that you want to change, you change it temporarily to a text file. So change the .afl to .txt. And when you do that, you are able to then open it with either a notepad, or you can import it into Excel where you can manipulate the data. Okay? As I said, the only thing Explain is concerned about is the data that occurs in those 4 columns. So when it reads, it needs to find those data points, 721 of them. So if the file didn't consist of anything other than the first 4 or 5 lines, and then followed by the header, Explain still works with it, because it goes down to the header for the data, which is alpha, CL, CD, CM. Which is that header. So it reads the file, gets to that point, and then it starts to read the data from that point onwards. Generally speaking, you don't need to modify anything other than the data points that you need to manipulate. So now let's look at a utility I developed that allows us to modify the data directly. By the way, the utility is being made available online, so if you want to use it, you may do so. It's called Airfoil Data Viewer. I developed it a few years ago, and all that allows you to do is read any airfoil file. Let's say we read a GOE 488 test airfoil, and it does exactly what Airfoil Maker does. It reads the data point and it creates the graphs for you. It's a single Reynolds number. Okay, but the good thing here is that I can change any data point directly. And once I've changed the data point, I can save the data file and Explain is able to work with it. Okay, so much easier way of changing the information directly. So I'll let everybody have a little play with this tool and see what you think. Again, the CL versus alpha is presented as the green line. The CD versus alpha is presented as the red line, and the pitching moment characteristics are presented as the blue line. So you can scroll down the data points and literally change any data point you want. So for example, if you want to change the lift coefficient at 0 alpha, so scroll down to 0. So let's change that number to 0.5, just for the hell of it. So you can see immediately I produced a little spike. So the number's been changed. So if I now save that information, then I'm able to use that airfoil file in Explain. So I can modify any or one or more than one data points across the 3 folders. The other thing that you can do with this application is to load from either Xfoil or XFLR5 a table of values from, let's say, 20 degrees minus to plus 20 degrees for CL, CD, and CM, and incorporate that into this program and save it for use in Explain. So as I said, from minus 180 to minus 21, flat plate is as good. And from 21 degrees to plus 180 degrees, flat plate is as good as. So what we're really interested in is minus 20 to plus 20, and that really should be your airfoil.
Big amount.
Okay, so that will define it, and will, Explain will work quite well. Okay, so again, if you have a symmetrical airfoil or a flat plate, then generate the data between minus 80 to minus 21, plus 20 to plus 180 for each Reynolds number, and then in the middle, generate it for the airfoil that you're interested in, and it works quite well. Okay, so I'll let you guys play with this application for a little while, a few minutes, and then we'll move on. So what we are trying to do is, for people who are online and people who are present in the room, we're trying to modify the data using my program. A few data points, change a few data points, save the data file, and then open the file again in Airfoil Tools or Airfoil Maker and see if that change has taken place. Now, the reason why we're doing this is Explain doesn't have a very large bank of airfoils as default. So when you launch Explain, it has a few 63 series, it has a Clark Y, and it has some symmetrical airfoils present. If you are embarked upon a new aircraft design, then the chances are that you're not going to have that AFL file that you're wanting to use. So therefore, if you get a little familiar with using the airfoil maker and other tools, then that will certainly help in speeding up the process when it comes to aircraft design. What we'll be looking at in a little while, XFLR5, where most of this data can be generated, then manipulated in Excel to be incorporated into the .afl file for use in Explain. Okay, so we'll go through that process as well. But for now, I think it suffices that you can see that if you modify the airfoil file, then when you externally, so long as the file structure is kept the same, Explain is able to work with it. Okay, that's the important take-home point. Now, for those of you who are interested in this little applet that I have developed, at the moment, it only deals with one Reynolds number. So if you only had just one Reynolds number, it will deal with it. I am currently working on a file that will allow up to 10 Reynolds numbers to be dealt with, as it were. Okay? So you'll be able to create a composite file consisting of up to 10 Reynolds numbers or polars corresponding to 10 Reynolds numbers. Okay, and that will be made available as soon as I'm done with it. Hopefully, maybe another couple of weeks' time. But this application is available. It was uploaded to the chat section, so you're free to use without any problems. Okay, should be able to modify any AFL file with Explain or in Explain, as long as it's not got more than one Reynolds number. Right, just again to reiterate, if you modify the data using my applet, then you need to save the data before you can read it back into Airfoil Maker. Okay, so modify the data, then save the data, give it the same file name or a new file name. It will by default save it as a .afl that is used by Explain, and then if you read it again using Airfoil Maker, then those changes would be reflected. The limitation of this program is, as I said, it will only work with one Reynolds number. I am working on an application that will allow up to 10 Reynolds numbers to be manipulated simultaneously. Okay, so that'll be a little bit more comprehensive than this basic application. Okay, also I will have the ability in that program to splice the data directly. So for example, when you generate the data in XFLR5 or Xfoil between say -20 to +20, you should be able to splice it directly into the file and save it for use by Explain. So just give me a couple of weeks, then hopefully you should be able to produce that application, which will make life a lot easier when working with Explain and Airfoil Maker. Okay, right, what we'll now do is take a 10-minute comfort break, and then when we come back, we will have a look at XFLR5, and then maybe play around with 5 or 10 minutes using Explain. Okay, let's have a 10-minute break. Welcome back. I hope you've had a decent break. We are going to be using for the next 20 minutes, 25 minutes, a program called XFLR5. Now, again, just to sort of reiterate, last time we met, we created a fairly rudimentary aircraft using a 2410 airfoil and a symmetrical for the empennage. And we found that the aircraft does fly, and it's okay. It's not one of the world's best aircraft, but nevertheless, it flies reasonably well. So the idea is that for the next session that takes place in May, you're able to modify either that aircraft to make it look resemble what you wish to fly in the simulators, or come up with your own aircraft. If you're going to design your own aircraft, and if you didn't have an airfoil file in Explain, then the purpose of this session was to get you guys to design your own airfoil or modify the data for a chosen airfoil so that you can use it in your design. So we can use either Airfoil Maker to create your own airfoil through curve fitting techniques, or you can splice the data. The data could be generated using XFoil or XFLR5 or airfoil tools online between -20 to 20 degrees with an increment of 0.1 degree alpha. And that will work quite well. You could literally take any airfoil from X-Plane database of airfoils and splice between -20 to 20 the data for your airfoil, and that will work equally well. Okay, so what we're now going to do is use XFLR5. So if you haven't installed XFLR5, the zip archive was put on the chat. So you download the zip archive to your machine, double click the zip archive, that will open up the archive, which you are then able to copy onto your desktop. So the process will be, there will be a zip archive either on your desktop or in the Teams chat window. Double click. The program that we need to invoke is XFLR5. And when that opens up, it opens up with just a very simple menu option. The file menu, the module menu, and the options menu. So for example, when I click the file menu, it will ask me to open up a new project or an existing project, open up the last project that you were working on automatically, etc. So basic file input output options in that menu. The next menu is the 4 principal modules used in XFLR5. The first one is what we call the direct foil design. And what that is, it gives you the ability to create arbitrarily any airfoil shape you wish. Okay, so we'll have a little play with that. And that is done by fitting through a set of data points, generally about 5, some nice bicubic splines. So when you pick the bicubic splines, we are able to create any airfoil shape, both the upper surface and the lower surface, by dragging those points around. So we'll have a little play with that. The next option is what we call the inverse design. So provided we have data generated for an airfoil, and if we wanted to change, let's say, the velocity profile over the airfoil, then we're able to specify what profile we want, and then XFLR5 actually then generates the data points for the airfoil that will allow us to produce that velocity profile over the airfoil. Okay, so that's called the inverse design. The third module is the most useful module, I guess. It allows us to create the data needed for X-Plane in terms of your CM, CL, and CD. So we'll use that to start off with. So if I click that, it will show me all the folders. But since I have not defined the airfoil yet, so what I need to do is I need to look at the various menus now that have come up. The module that I clicked was XFoil Direct Analysis. That is what I have clicked. And as soon as I've clicked it, further options are now available. So for example, the view option allows you to look at any operating point. So for example, if you've generated a set of curves, so you can select which a point that you are interested in. The polar view just allows you to look at the lift, drag, and pitching moment curves. The foil design allows us to merge various foils, so those menus can be invoked as well, plus the design menu allows us to create the new airfoil. So for example, if I choose the NACA foils, I can generate all the 4 and 5 series NACA foils. So let's say if you want to generate a symmetrical airfoil, 006, let's say, and I'm going to generate 100 panels. .006, not 060. Okay, so I have defined an airfoil. That's a 006 NACA. Now to perform the analysis on this airfoil is rather simple. We go to Analysis. And in the Analysis menu, you define an analysis. When we define analysis, another box or another window pops up. Here we can specify whether it is a type 1 analysis, type 2 analysis, type 3, or type 4. Now what they refer to is type 1 analysis is a constant speed analysis. Type 2 analysis is a constant lift analysis. Type 4 is looking at the side slip, and I believe type 3, the angle of attack. So for our purposes, for generating the CL-CM-CD, we need to do a type 1 analysis. We also need to specify the Reynolds number. So in the box below here, we can specify the Reynolds number. It's currently at 100,000. The other boxes, I suggest we leave untouched. The most crucial one amongst those 3 here are the N crit. This is the point where laminar to turbulent separation occurs. So that number needs to be 9. The lower the number, the more turbulent the flow, etc., etc. So leave N crit equal to 9 for most purposes. Once you've defined that and clicked OK, you will see that the box on the right-hand side, which is the direct foil analysis towards the right top-hand corner, the Analyze button has become bold. Now I can do the analysis. At the moment, it will start at 0 degrees and it will go to 1 degrees with a 0.5 degree increment. So if I want to sequence it, I click the sequence box. I can go from, say, 0, and I can go up to 20 degrees. And perform the analysis. What has it happened? So it's generated the CP versus alpha for all those AOAs from 0 to 20 degrees. So if I wanted to reduce the data that I'm looking at, I go to the left-hand window and switch off any plot that I don't want to see. But not only that, what you're able to then do is to look at the animation. So we'll now go from 0 degrees to 20 degrees, and it will dynamically update the CP versus alpha curve for each operating point. And it'll also give you the pressure distribution and give you the information on the turbulence or the wake. So for example, the red curve is the flow. You look at the separation. So as it gets bigger, the flow separates a lot earlier. So fairly straightforward in use. So make sure that you have the store operating point menu item clicked before you do the analysis. Otherwise, it doesn't store the data points. Now, as part and parcel of the files that I uploaded this evening, you will see a file called LADG, Light Aircraft Design Group. So if you were to open a file, open a project, the LADG is a valid file that consists of the NACA 2410 as well as the symmetrical airfoil NACA 0009 that we used in our design. Now to save the data, again, it's very simple. If you go to the polars and say export, we are able to export this data that you've generated between 0 and 20 degrees as a text file. So we haven't got a lot of time, so what we'll do is very quickly go through the other options as well. So I'm going to load the data file LADG, and there you will see that I have the NACA 2410 and a NACA 0009, which I've used for the vertical and the horizontal tail. So that file should be with you. If you haven't, please do shout, and I will make sure that file is available online as well. Okay, one of the things that we like to do with XFLR5 is also do the stability analysis. Okay, so we need to define an aeroplane, and we then need to use these airfoils that we've created, and then use that in our stability analysis to give us an idea whether the aircraft is stable or not. Now, to do that, we need the wing and plane design module. And what I was able to do was to create the wing, the empennage, and the vertical fin. I will show you exactly how that is done. It is very simple. Once you invoke the plane design module, which is that module there, further menu items come up, which is view, and the plane menu comes up along as well. So if I say define a new plane, or I can modify an existing plane, then to modify the existing plane, right click the mouse button When you right-click the mouse button, a menu item shows up, and we can look at the current plane that is in view. And using the submenus, we can either perform the analysis on this plane or we can edit the plane. So if I click edit the plane, then it gives me the opportunity to modify either the main wing. Now, sadly, the word elevator is being used. It's not really elevator. The word really should be horizontal tail. So we're designing a horizontal tail. We're not designing a control surface. So that's a little bit of a problem with XFLR5. We're not designing the elevator. We're actually defining the horizontal tail. We can define a fin. So we can define a conventional aeroplane, fin, horizontal, as well as the main wing. But fortunately, it also has the ability to define a second wing. So we can look at either biplanes, or we can use that second wing to define a canard. So we can look at a canard or a biplane or a conventional design. Okay. Now, in terms of the configuration, a T-tail is possible, a conventional cruciform tail is, empennage is possible as well. You can mount the wing high, mid, or low. So those permutations in terms of the geometry and the layout are still very much possible in XFLR5. So to modify any element, whether it is the wing element or the fin element or the horizontal tail element, we click the define button. When we define it, it brings up another menu item, which allows us to create the chord at the 0Y position. The 0Y position, don't forget, will be the root. Okay. So define the tip Y position. Now, remember, we used a 7.7 meter wingspan for our aircraft last week or last month. So 3.720 is the tip point, and the root and the tip are 1.24 meters in chord. So it's a planform wing. So if I change, let's say, the tip chord, you can see the effect. You can now create taper. Go back to 1.24, and it becomes a planform. If I want a dihedral, then I basically create a dihedral. That's fairly straightforward. Just enter a number, and the wing will have the dihedral you want. The other important things is how many panels you need to predict the aero behavior. If there is a discontinuity, for example, you might decide that the wing has a planform section and the outer section has a dihedral. So, for example, so the wing curves up. Then at the junction of the flat or planform wing to the dihedral wing, you need a lot more panels. So these number of panels in the chord-wise direction and the span-wise direction are then important. So you need more panels for the program to be able to predict the aero behavior correctly. Now, because it's a rectangular wing, the default number of panels, it's saying it will need around 13 panels along the chord, and it will need around 5 panels along the span. You can increase it increase it to say maybe a 10 panels, press enter to select the foil. And of course, it will be uniform distance, or uniformly spaced. So once you define that, it should be able to work quite nicely. Similarly, we can define the empennage, which is the horizontal tail, exactly the way we've defined the wing. At this juncture, we need to also specify some of the inertias. If you don't specify the inertias, then of course your Ixx and Iyy values are going to be wrong, and from a stability point of view, you're going to get completely misleading results. So you need to get the inertias more or less right. So how do we define that? So if I go to my airplane design, right click, current plane, and plane inertia. That's where I need to be. When I click the plane inertia, then I can specify the mass for the wing by clicking the main wing. And what I have now got is the mass of the wing to be 200 kilograms. And then I've also estimated the mass for my servos and actuators and my control surfaces called ailerons. So I've got two masses on the extremities of the wing, so where I can specify the X and Y location of the masses and how much mass we have. So what we're looking at is defining in XFLR5 point masses, okay, along the wing, along the fuselage, and on the empennage. So these masses can be defined anywhere you like, and as many masses as you want. The more you'll have, the better approximation you're going to get for the inertia, especially Ixx and Iyy. Okay? And of course, Izz as well. Now, there is no concept of fuselage in XFLR5. In fact, there is an option in the main design menu to look at the fuselage. But if you click on the fuselage option, unfortunately, XFLR5 has kittens and doesn't converge. So I would leave that option unclicked and just define the point masses to represent the inertia for the various fuselage elements. So if you define the front section, middle section, and the tail section, that will give you a reasonably good approximation for the inertia, especially when we are looking at Izz for the inertias. Okay, so we need that. And to define that, it's a case of defining the mass, defining the X location in meters, the Y location in meters, and Z location. So by defining the X, Y, and Z, you can place the mass wherever you want within the design. Okay, so once all is done, then all I need to do is do the analysis. So go into plane, define an analysis. I'm going to do a type 2 analysis, which is the constant lift analysis. And when I do that, I am able to run the analyze or analysis. And once the analysis is done, it is pretty quick. What you'll see is it will give you the inertias. It will also give you the various stability derivatives. And it will also give you the eigenvalues associated with the longitudinal and the lateral modes. Later on in the evening, once the session is finished, which is going to be in a few minutes' time, I will upload on the chat a few links where there are fairly good videos online on YouTube. There is, I believe, a series of about 10 or 12 videos, anything ranging between 5 minutes to 15 minutes, on various aspects of XFLR5. Now, I strongly recommend that you go through those videos, and they will be very, very helpful in you trying to understand how XFLR5 works. So what XFLR5 allows you to do is to perform the aerodynamic analysis to give you the CL, CD, and CM values for the chosen airfoil. You can do a reverse design, you can do a direct design, and you can also define a plane in terms of the layout and perform a stability analysis. Now, the aircraft that we have will be seen to be stable, and it has more or less the same performance as what X-Plane predicted in the last session. Okay, it's not quite there, but because we haven't defined the inertias in the LADG file as closely as it needed to be. So anyway, thank you very much for being with us today. I hope it's given you some idea as to what's involved in creating the files. We had a very brief run in with XFLR5. I wish we had more time, but if there is a demand, then we can run additional sessions in the future in the use of XFLR5. That's not a problem, but I would recommend strongly using the videos online to get to grips with XFLR5. Okay, right, thank you very much indeed. If there are any questions, keep posting them on the chat. We should be able to address them so long as the chat is open. Thank you and have a very good evening.